2 Tuesdays ago, while the entire world had its eyes locked on a disaster unfolding in Japan, a fault that almost no one in California even knows exists quietly slipped for the second time in just over a month. And the way it moved should have made national headlines. Within a matter of hours, the United States Geological Survey had logged more than 160 separate tremors tied to that single event, and they attached one word to it that changes everything about how you should read this story. They called it a potential main shock. That one word, potential, holds the entire weight of what science does not yet know. This fault points like an arrow straight toward the Bay Area, and buried in the layers of Earth beneath it is a record of ruptures far bigger than anything modern instruments have ever measured there. Stick with me to the end, because I'm going to walk you through exactly what this fault has done in the past, and the single warning sign that tells us what might be coming next. And if this is the kind of story you want to understand before the news catches up to it, do me a favor and subscribe, because this is the stuff that matters. It happened at 40 minutes and 6 seconds past 7 in the evening, Pacific time. The ground about 5 miles to the east and slightly south of a small town called Cloverdale, California, simply broke. The Geological Survey first measured the quake at magnitude 4.2 and bumped it up to 4.3 within the hour as more data came in. What really caught the attention of the people who study these things was how shallow it was. The rupture happened only around 3.5 miles beneath the surface. In the world of earthquakes, that's practically at your feet. One regional catalog places it a touch deeper, closer to 4 miles, but either way the break occurred inside the brittle upper crust, the layer where the shaking hits hardest for the energy released. That shallowness is why people felt it so strongly for such a modest magnitude. Nobody was injured. No buildings collapsed. The survey's automatic impact system flashed a green alert for both potential deaths and economic damage, which is the calmest reading the scale can give. Even so, more than 500 people took the time to report feeling it. The reports came in from towns right next to the epicenter, places like Healdsburg, Geyserville, Middletown, and Kelseyville, and they also came from much farther out, from Roseville, Elk Grove, and even San Francisco, well over 60 miles away. The strongest shaking anyone recorded reached a level 5 on the intensity scale, which sounds dramatic, but really just means dishes rattling in the cupboard and a picture frame or two tilting on the wall. Nothing structural, nothing dangerous. On any ordinary week, a magnitude 4.3 in Northern California is a footnote. It earns a short paragraph, a little map graphic, and then it vanishes from the news cycle by morning. But this one is genuinely different, and it's different for 3 very specific reasons. None of them have anything to do with how hard the ground shook. The first reason appeared quietly in the survey's own data feed within hours of the rupture. And honestly, it's the number that should have turned this into a national story. The agency did not treat the Cloverdale quake as a one-off. It labeled it the potential main shock of an entire earthquake sequence. More than 160 individual seismic events were tied to that sequence in just the hours after the first break. That figure came straight from the survey's earthquake sequence tracking product, and it's the single most important detail in this whole story. Let me explain why. The number of aftershocks a quake produces scales with the size of the main shock. For a magnitude 4.3, you'd normally expect just a handful of tiny follow-up tremors, maybe a dozen at most, fading away fast and quiet. A sequence in the hundreds is a completely different animal. That's what scientists call high productivity, and high productivity tells you something very specific about the rock down there. Here's the difference. When a single stuck patch on a fault fails cleanly and then settles down, you get a small crowd of aftershocks and it's over. But when a wide volume of crust is already sitting right on the edge of failure and one piece finally gives way, the sudden shift in stress lights up everything around it like a chain of dominoes. That's what 160 events actually represents. It isn't one patch breaking. It's a whole section of the Earth's crust actively rearranging itself. And the survey's forecast added something concrete to watch for. They expected at least one aftershock of magnitude, 3 or larger within the following week. That window opened that Tuesday night, and as of now, several days of it still remain. None of this would carry much weight if the quake had struck somewhere anonymous and forgettable. It didn't. And that brings us to the second reason this matters. The Cloverdale epicenter sits on a fault system called the Maacama, and unless you work in seismology, you've almost certainly never heard the name. The Maacama is a right lateral strike-slip fault, meaning the two sides grind past each other sideways, and it runs from the northwest to the southeast through the coast ranges of Northern California, sitting east of the far more famous San Andreas. It tilts somewhere between 50 and 70 degrees into the Earth, and it carries a serious chunk of the grinding motion between the Pacific and North American plates through this part of the state. That motion has to go somewhere, and the San Andreas alone simply doesn't absorb all of it. The Maacama moves at roughly 9 millimeters a year, give or take 1.5 millimeters, according to the deformation model built for the National Hazard Assessment. For comparison, the San Andreas offshore of the same region moves at about 24 millimeters a year, the fastest rate on the local map, And yet, that offshore stretch has produced almost no cataloged quakes at all. The Maacama also does something called creeping. Creep is slow, steady, silent movement, the two blocks of earth sliding past each other without ever producing a jolt you can feel. On the Maacama, that creep happens at somewhere between 2 and 6 millimeters a year. You can actually see the evidence in the landscape. Curbs and pieces of infrastructure that cross the fault line have been visibly shoved sideways over time. Now, creep often gets described to the public as a kind of pressure release valve, and that framing is where all the false reassurance comes from. It's badly incomplete. The researchers who studied this fault's recent behavior put it bluntly. Yes, creep bleeds off some of the seismic energy, but strain is still building along this fault, and that strain will eventually come out as earthquakes. Do the simple math. If the fault moves 9 millimeters a year, and creep only accounts for 2 to 6 of those millimeters, then somewhere between 3 and 7 millimeters a year is not being released quietly. That leftover motion piles up as stored elastic strain inside the rock. It doesn't vanish, it just waits. The third reason this quake matters is that it wasn't the first. Back on the morning of the 24th of June this year, at 10 minutes past 8 local time, a magnitude 5.6 struck near a town called Ukiah in Mendocino County. The epicenter sat directly beneath a Buddhist monastery in a thinly populated stretch of forested mountains. It was the largest quake that region had seen in nearly 90 years. More importantly, it was the largest quake ever attributed to the Maacama fault in the survey's entire recorded history. Close to the epicenter, the shaking was severe. Instruments within about 6 miles measured intensities between 6 and 8. The survey's model estimated that around 10,000 people felt level 7 shaking. More than 4,500 felt reports poured in. Thousands of Mendocino County residents lost power. There was minor damage, and there were injuries. And the fault signature matched the Maacama precisely. The orientation of the rupture, running northwest to southeast and tilting 54 degrees, lined up perfectly with both the pattern of small quakes seen in cross-section and the fault geometry that had been mapped independently by other researchers. So, put the pieces together. The Maacama produced the largest quake ever recorded on it on June 24th. Then, 34 days later, it produced a magnitude 4.3 with a swarm of more than 160 events, about 35 miles to the south, along the very same structural trend. 2 significant quakes, 5 weeks apart, on a fault that had never once produced a cataloged event above magnitude 5.6 in the entire history of instrumental recording. Now, let me be careful here, because this is exactly where the clone channels go wrong. This does not mean a giant earthquake is on the way. The instrumental catalog is short, and short catalogs constantly throw up what look like dramatic changes, but turn out to be nothing more than the illusion of a small sample. What it does mean is that a fault the public has never heard of has now, twice in 5 weeks, made it clear that it's up to something. The June quake also taught a second, more uncomfortable lesson, and it's about our warning systems. ShakeAlert, the earthquake early warning network that blankets the West Coast, is the most advanced public system of its kind in the entire Western Hemisphere. And on June 24th, it worked exactly as designed. It detected the rupture. It fired off an alert. Roughly 657,000 warnings went out through the MyShake app. And here's the catch. The people standing in the zone of the very strongest shaking got their alert after the strongest shaking had already reached them. The first ShakeAlert message went out 5.5 seconds after the earthquake began. In 5.5 seconds, the seismic energy has already raced outward about 11 miles in every direction. Everyone inside that circle was already being shaken before the alert even existed. Then add on transmission time. The cell networks, the app delivery, the phone buzzing in your pocket. That blind zone stretches even wider. The researchers who documented this stated it plainly. These systems are not predictors. They are detectors. They will never manage to warn the people sitting right on top of the epicenter in time. And that isn't a flaw in ShakeAlert. It's a description of physics. An earthquake has to actually start before anything on Earth can detect that it started. The warning travels at the speed of light. The damaging waves crawl along at just a few miles per second. So the farther you are from the rupture, the more warning you get. 30 seconds of heads up in San Francisco for a distant quake genuinely saves lives. But directly above the fault, there's no beating the math. The popular idea that early warning is a form of prediction is simply wrong. And June 24th is the clean, documented case that proves it. 5.5 seconds to the first alert. 11 miles already shaking before it fired. Now, while they were studying the pattern of quakes around that June rupture, the researchers tracking this fault noticed something they couldn't identify at all. There's a clear band of earthquakes sitting between the Maacama and another fault called the Bartlett Springs. It shows up sharply in the catalog, a straight-line concentration of events, which is the classic fingerprint of an active geological structure. But here's the strange part. It doesn't appear as a mapped fault in the national database of faults considered active. The California mapping shows some structures in that area, but marks them as inactive. Two working seismologists actually went public and asked for help figuring out what it was. A reader pointed them to a paper from over a decade ago, and a third scientist independently pointed to the exact same paper. Sit with what that means for a second. There's a prominent seismically active structure in the Northern California coast ranges that isn't fully accounted for in the National Inventory of Active Faults. It's not hidden. It's not a cover-up. The earthquakes are sitting right there in the public catalog for anyone to see. They just haven't been assigned to a named fault yet, and the Maacama's true story runs much deeper than its short catalog suggests. Careful digging into ancient sediment layers near a town called Willits turned up fault offsets that point to several large earthquakes on this fault within the last 1,200 years. That study deliberately refused to assign magnitudes because turning a single measurement of ground offset into a magnitude number just isn't defensible science. But the researchers who reviewed the record, while being upfront that they were only estimating informally, put the likely size at magnitude 6.5 to 7 or larger. Their reasoning was simple. Smaller earthquakes don't leave any preserved geological record at all. So whatever carved those marks had to be big. Now think about the energy scale, because it's logarithmic, jumping roughly 30 times with each whole unit. A magnitude 6.6 releases about 30 times the energy of the June magnitude 5.6. So this is a fault that creeps, that supposedly bleeds off pressure, and yet still leaves ruptures that size buried in the sediment. That's a fault where creep is nowhere near enough to keep it quiet. Follow the trend southeast from where all this activity is happening, and it stops being an abstract puzzle very quickly. The mapped Rodgers Creek fault begins in the general area of this recent sequence and runs to the southeast, straight through Santa Rosa and toward the Bay Area. For decades, scientists had an open question about what happened to that fault when it hit San Pablo Bay. Then, imaging beneath the surface finally answered it. The Hayward fault and the Rodgers Creek fault are directly connected underneath the bay, with the Hayward bending about 10 degrees as it crosses. They are, in fact, one continuous structure with a combined length of roughly 118 miles. The maximum modeled magnitude for a rupture running that entire connected length is 7.4. That number needs an immediate qualifier, and the survey is very clear about it. Ruptures that break across multiple fault segments are real, but they're considerably rarer than a single fault breaking on its own. The full 7.4 scenario is less likely than the individual Hayward scenarios, which model at magnitude, 6.8, and 7.0. And those are already among the most serious earthquake scenarios anywhere in the United States, because the Hayward runs directly beneath the densely packed East Bay. A magnitude 7.4 would release something like 700 times the energy of that June quake near Ukiah. Let me be completely clear about what I am and am not claiming here, because this is the line the accuracy matters most. A magnitude 4.3 near Cloverdale does not load up the Hayward fault. There's no physical mechanism by which it could. The connection here is structural, not causal. What matters is that this sequence is happening on the northern tip of a fault system that runs unbroken into the most densely populated corridor in Northern California, on a segment whose ancient earthquake record runs 2 full magnitude units larger than anything in its modern catalog. There's one more thing to clear up before we leave California. There's a second cluster of quakes visible in the same map view, over near Clear Lake at a place called the Geysers. This is the largest electricity-producing geothermal field in the entire world, and what's happening there is a completely different phenomenon. When you pull steam out and inject fluid back in, you remove mass and heat, the reservoir rock contracts, and that contraction produces tiny earthquakes. That kind of human-caused seismicity is real and openly acknowledged, but it's confined to the reservoir itself. It's shallow, small, and tightly bounded in space. The Cloverdale sequence is on the Maacama, and the June rupture was more than 35 miles to the northwest of it. Clear Lake itself is a volcanic field that hasn't erupted in thousands of years and is showing zero signs of doing so now. 2 entirely different processes, just sharing one map. Now, for the reason none of this made the news in the first place, roughly 27 hours before the ground moved near Cloverdale at 4 in the afternoon Japan time, a shallow quake ruptured beneath Kumamoto Prefecture on the island of Kyushu. Japan's agency measured it at magnitude 7.1, and the survey later revised it to 6.8. It struck about 6 miles deep, and crucially, it happened inland, not on the offshore subduction zone. It registered the maximum possible reading on Japan's seismic intensity scale in 2 locations. That maximum reading has only been hit a handful of times in the scale's entire history, and this was the first instance since a devastating quake in early 2024. A tsunami advisory went out within about 2 minutes, forecasting waves up to 1 meter, and it was lifted around 2 hours later. There was no destructive wave and no threat to the west coast, but the damage on land was severe. There was at least 1 confirmed death by that evening, a person pulled from a collapsed home who later died in the hospital. Somewhere between 20 and 30 employees were unaccounted for at a shopping mall in Kumamoto City, where part of the second floor caved in. Then, about an hour later, an explosion tore through the complex, blowing out walls and exposing the steel skeleton of the building. Witnesses said they smelled gas, though the official cause is still undetermined. Heartbreakingly, that mall had reopened just 6 weeks earlier, rebuilt after a previous earthquake years before. One hospital reported more than 50 wounded, another around 40, including 10 in serious condition. Roughly 300,000 people were sent to evacuation centers. Fires burned in the city. Sections of the expressway split apart. Part of the wall around the historic Kumamoto castle collapsed. The shaking was even felt across the sea in South Korea. That is where the cameras were, and rightly so. That is where the human suffering was. But Japan also hands us the case study that makes the California sequence genuinely worth taking seriously, and it comes from the exact same fault system. Years earlier, in April of 2016, a magnitude 6.5 struck those same fault zones beneath Kumamoto. Everyone treated it as the main event. Emergency crews mobilized. People went back inside their damaged homes. Then, 28 hours later, a magnitude 7.3 hit the very same system. The first quake was only reclassified as a foreshock, after the second one had already arrived. Both produced that maximum intensity reading. This is exactly why the survey's careful word choice on the Cloverdale event carries so much weight. They called that magnitude 4.3 the potential main shock of a sequence. That word potential holds the entire unresolved uncertainty of the whole discipline. Here's the hard truth. There is no physical property that separates a foreshock from a main shock at the moment it happens. None. You can only tell the difference looking backward in hindsight. Now, the base rates here are well established and, up to a point, reassuring. Following any given earthquake, about 6% of the time a larger event follows within 3 days, and about 5% within a week. That means 19 times out of 20, nothing bigger comes. And that probability doesn't change much across the magnitude 3 to 5 range. So a magnitude 4.3 is roughly 95% likely to be the biggest event of its own sequence. The reason to pay attention isn't that it probably won't grow. It's that the 5% case cannot be identified in advance by anyone using any instrument that exists. In 2016, the case was identified 28 hours too late. And in 2011, the catastrophic magnitude 9 off the coast of Japan was preceded by a magnitude 7.3 that nobody flagged as a foreshock either. Japan's own agency is applying that lesson right now. They've warned that strong aftershocks remain possible for a week, with the highest risk in the 2 to 3 days after the rupture. The Prime Minister publicly told residents in the hardest hit areas to prepare for another quake of similar size. That might sound like some kind of inside knowledge, but it isn't. It's formalized protocol, and that protocol exists in this exact form precisely because of what happened in 2016. By that evening, more than 60 aftershocks had already been recorded. The largest was a magnitude 6.1, which is almost exactly what standard statistics predict for a magnitude 7 main shock. There's a third reading to pull from that same 48-hour window, and it comes from the fastest converging plate boundary on the entire planet. Over the day and a half before all this, the Tonga Kermatic subduction zone produced a noticeable, spread-out surge in magnitude 4 and 5 quakes, on the order of 30-plus events across roughly 2 days. There were clusters to the north and to the south, with quakes at intermediate depths in between. Now, Tonga Kermadec pumps out 4s and 5s all the time. The plates there converged up to about 9.5 inches a year, faster than anywhere else on Earth. What is not routine is a dense, simultaneous cluster, mixing shallow and deep events all firing together in the same stretch of the subduction zone. But the genuinely fascinating observation isn't where the quakes are, it's where they aren't. A segment of the subduction interface, bracketed on both sides by those active clusters, shows essentially no earthquakes at all. Not in the last 7 days, not in the last 30. And that quiet gap sits precisely where the interface begins, where strain accumulates. A quiet segment can mean two completely opposite things, and telling them apart is one of the truly unsolved problems in all of seismology. It can be a gap, where the fault slides along smoothly and produces nothing because there's simply nothing to produce. Or it can be a locked gap, where the interface is welded shut and loading up silently, right until the moment it isn't. That same ambiguity is exactly what makes the California picture so hard to read. The San Andreas offshore of Northern California shows almost no cataloged activity, and yet it ruptured back in 1906 at magnitude 7.9. The absence of a signal, in a system you know for a fact is loading, is not evidence of safety, which raises the obvious question. 3 plate boundary readings all moved within 48 hours. Did one cause the others?